morning, good afternoon, and good evening. Thank you for joining us today. My name is Allie Kane, and I will be the moderator for our presentation. I lead the implementation side of Fluor's Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are always at the core of our success. As with the other webinars that we've given, this will be a technical presentation. Today, subject matter experts Patrick Goodman and Javier Fernandez will talk about what might be the most popular energy transition topic of the decade, green hydrogen. Patrick and Javier will talk about the drivers behind today's hydrogen hype and the various developing technologies that may help make our world more sustainable for future generations. Now to get started, we have 3 subject matter experts with us this morning. I'll introduce our main speakers, followed by our health, safety, and environmental topic speaker. First, we have Patrick Goodman. Patrick has over 15 years of industry experience and is recognized as one of Fluor's subject matter experts in syngas processing, process simulation, and hydrogen production. He currently serves as Fluor's hydrogen strategy lead. He has a Bachelor of Science degree in chemical engineering from the University of California in San Diego, and he's a registered professional engineer in the state of California. Patrick lives in Orange County, where he enjoys ocean-related activities, gardening, home brewing, and spending time with his family. Next, we have Javier Fernandez. Javier received his doctoral degree in chemical engineering in 2017 from the Delft University of Technology in the Netherlands. His PhD was focused on designing and developing new generation technologies using alternative forms of energy to effectively intensify chemical processes. Prior to joining Fluor in 2018, he worked in the chemical industry. He has been not only growing as a process engineer, but also following his passion to build a cleaner world. Javier believes we should spend all our energy to ensure that we and future generations can live on a healthy planet. In his spare time, Javier enjoys fitness, reading, barbecues with friends, and following the financial markets. And finally, for today's health, safety, and environmental topic, which is really going to set the stage for our webinar, I'd like to introduce another one of our hydrogen subject matter experts, Tapi Karim. Tapi is a process engineer with 20 years of experience covering a wide variety of front-end and detailed engineering projects. Over the years, she's been involved in design, safety studies, and pre-commissioning for projects ranging from petrochemicals to oil and gas. She's worked on projects all over the world with a wide variety of clients and has a Bachelor of Science degree in chemical engineering and is involved in renewables and sustainability-focused markets and green hydrogen technologies. Her hobbies include sailing, swimming, gardening, and city walks. And with that, Tapi, I'd like you to please unmute your line and start us off with a safety topic today.
Thank you, Ali. A big hello to everyone. Thank you for joining our webinar today. I'd like to start off talking about caustic safety. During the production of hydrogen through alkaline electrolysis, a caustic solution of 30% potassium hydroxide is commonly used as an electrolyte. So why do we need electrolytes? To answer this question, let's quickly touch on the electrolysis process, which splits water molecules into hydrogen and oxygen using electrical energy. Typically, a water electrolysis unit consists of an anode, a cathode, separated by an electrolyte. Potassium hydroxide electrolyte helps increase the conductivity of water from 5 microsiemens per centimeter to around 100,000 microsiemens per centimeter. At the cathode, water is split into hydrogen gas and hydroxide anions. The hydroxide anions then travel through the electrolyte and a diaphragm to the anode, where oxygen is released. So I'd like to highlight some of the potential caustic hazards of skin burns. By KOH spraying via leakages from flanges and equipment nozzles. Another potential hazard is KOH carryover. This can occur during maintenance activities, inadequate sampling, and insufficient procedures and training. Caustic burns can be severe, so it requires immediate rinsing with water for at least 10 minutes and to seek medical help. So how can we actually prevent these hazards from taking place? Some solutions are to actually design for maintenance, which can include easy access to equipment, adequate low point drains for proper emptying, and sufficient flush connections. We should also design for safe operation by using splash guards on flanges, having overfill protection, using level alarms, safe sampling points, safety showers with eye wash facilities, and use PPE, safety goggles, and protective clothing. So now I'd like to hand over to Patrick, who will discuss other key aspects of green hydrogen.
Thank you, Tapi. Thank you, Ali. Today, Javier and I are going to talk about green hydrogen, what it is, including a brief history, a look at today's market and future outlook. Then we'll get into some of the underlying electrolysis technologies, explore some of the costs, and finally look ahead to using green hydrogen at scale. Before we get too far into what green hydrogen is, we have to ask, why green hydrogen at all? Simply put, business as usual is no longer acceptable. As a guiding document in the energy transition, the Paris Climate Agreement aspires to limit global temperature increases to 1.5 degrees Celsius above pre-industrial levels. Projections indicate that to achieve this goal, we must dramatically reduce emissions immediately and ultimately get to net zero emissions overall. As can be seen in the chart shown here, we are currently not on track to meet this goal. This requires a radical change in the way we produce and consume energy. A multifaceted approach is required, and green hydrogen is a piece of the puzzle, especially for hard to decarbonize sectors. While hydrogen is a colorless gas, the industry has adopted a framework of colors to describe the source of hydrogen and implicitly its carbon intensity. Most hydrogen today is produced from fossil fuels, where CO2 is emitted to the atmosphere. This is called gray hydrogen, or sometimes brown or black, depending on the type of feedstock utilized. Blue hydrogen is also fossil-based, but utilizes carbon capture and sequestration technology to reduce total emissions. Green hydrogen most often refers to hydrogen produced by electrolysis, using renewable energy, and will be the focus of today's presentation. Hydrogen from renewable natural gas or biomass gasification is also sometimes referred to as green. Check out an upcoming Innovation Builders webinar for more information on biomass gasification. Other colors include turquoise, pink, and even yellow, purple, or white hydrogen. By and large, though, gray, blue, and green are most commonly used. Currently, the hydrogen market is a $120 billion industry. Annual global demand for pure hydrogen is approximately 75 million tons. Hydrogen mixed with other gases represents another 45 million tons of demand. Steady growth in the market has existed for several decades. Pure hydrogen growth has been driven primarily by captive users in the refining and fertilizer sectors, while hydrogen mixed with other gases has seen increased consumption for methanol production and as a byproduct fuel gas. Virtually all of this hydrogen is gray hydrogen, produced from steam reforming of natural gas or gasification of coal feedstocks. Looking forward, production and use of gray hydrogen is expected to be displaced by a mix of blue and green hydrogen, with very little gray remaining beyond the year 2040. This is driven by hard to decarbonize sectors where it's challenging to simply decarbonize by electrification. Examples include existing refining and ammonia capacity, the steel industry, heavy duty and long haul shipping, aviation perhaps, seasonal power storage, and other industrial processes where CO2 can be utilized in conjunction with the produced hydrogen. The actual proportion of green versus blue hydrogen as we move towards 2050 will vary, depending on the variety of considerations, including technology cost, cost of carbon, and other regional considerations. Now you might say, haven't I heard this before? And you'd be right. The idea of a hydrogen economy goes back to about 1970. The oil embargo in the 70s led to quite a bit of interest in alternative energy, including hydrogen. After the embargo was lifted, though, oil prices fell and interest for alternatives like hydrogen with it. Then, in the 1990s, fuel cells took the spotlight, especially in the auto industry. Again, oil prices remained low and interest waned. The 2000s saw another boom and bust. Now we are in 2021, and Wood Mackenzie has called the 2020s the decade of hydrogen. You can hardly go a day without a new project announcement around hydrogen. So what's different this time? Certainly a strong push to limit carbon emissions from governments, industry, and individuals alike. But perhaps even more significant is the proliferation of cheap, renewable energy. Dramatic cost reductions in solar and wind are really what can turn this latest round of hype into reality. As you can see from the chart, even 10 years ago, the costs of renewable energy put green hydrogen well out of reach. Today, though, wind and solar represent the majority of new electric generating capacity additions, while traditional technologies, such as coal, are seeing early plant retirements in many parts of the world. Now that we've generally introduced green hydrogen, Javier will dive into the technology behind its production.
Let's go straight into the presentation and talk about what electrolysis technology is and its long history, as well as the different types of electrolyzers available in the market. Electrolysis is becoming more and more popular on the news. We see new announcements on a weekly basis, but electrolysis is not a new technology. Electrolysis has been used for more than 100 years to perform chemical reactions using electricity as an energy source. Here we can see 3 examples. 2 plants producing green hydrogen in Norway that ran for 40 and 60 years, proving the strong reliability of this technology. Another example of green hydrogen production is found in Peru, to make green ammonia with a capacity of 50 tons of ammonia per day, with green ammonia being one of the largest potential off-takers of new green hydrogen capacity. We can conclude that electrolysis is not a new technology, and there is plenty of experience developed over the years to ensure a successful implementation of this technology at large scale. If there is a process where electrolysis has been widely used globally, it's in the production of chlorine, known as chlor-alkali electrolysis technology. Chlor-alkali technology has been in operation for more than 100 years, with plants all over the world. This technology is the sister of alkaline water electrolysis for hydrogen production. And there are many similarities between the two, which will certainly help speed up the implementation of water electrolysis at large scale. On the left-hand side, you can see an electrolytic membrane cell. This technology works as follows. A high concentration solution of sodium chloride in water is fed into the electrolysis cell. And then by applying a current, sodium chloride is split into chlorine, hydrogen, and sodium hydroxide. Here we can see an example of a chlorine plant in the UK producing roughly 400 kilotons of chlorine a year, which is equivalent to 125 megawatt capacity. Fluor has executed chlor-alkali plants across the globe, and this plant is one of them. Now let's figure out how we can produce hydrogen using water electrolysis technology. In this diagram, you can identify the main elements of a water electrolysis plant, including the power generation from wind, solar, or other renewable sources, as well as the electrical equipment required to get the power at the right conditions for the electrolyzer cells. Then we have the feed water supply, which is the main raw material together with electricity. Ultra-pure demineralized water quality is required to run the electrolysis unit, with preferred electrical conductivity of 1 microsiemens per centimeter. Although alkaline technology can handle water with higher conductivity values, up to 5 microsiemens per centimeter, compared to proton exchange membrane technology that has more stringent water quality requirements of 0.1 microsiemens per centimeter. Here we have the electrolyzer stack. This is the heart of the plant, where the reaction takes place splitting water into hydrogen and oxygen. Let's take a moment to understand what the term stack means. A stack is a combination of multiple cells, like the one we have seen for chlor-alkali technology, all placed together in series within a frame. On the right-hand side, we see an example of a stack for proton exchange membrane technology. The top image shows two cells, each composed by a membrane and two electrodes. In the same image, we also find a bipolar plate in combination with a porous transport layer used to separate each of the cells. At the streams, we have the end plates, which are very important to avoid leakage and collect the outgoing fluids. The bottom image displays two stacks for proton exchange membrane technology from the British company ITM Power. The lifetime of the stack is an important aspect to consider because degradation affects the stack elements and therefore its performance and efficiency. As a result, the stack needs to be entirely replaced, which impacts the maintenance costs and the CAPEX of the plant. As a reference for alkaline electrolysis technology, the lifetime of the stack varies between 10 and 15 years, so you can count on replacing all the stacks once or twice in the lifetime of the plant. Back to the main process, we have the downstream equipment required to produce hydrogen at very high purities of 99.99%. As part of the purification section, there is a separation step to remove the condensate formed after the hydrogen stream is cooled down, which is then followed by a deoxidation step to remove oxygen contaminants, and a final drying step to remove the free water still present in the hydrogen stream. Additionally, depending on the type of technology, you might need a compression step to get the hydrogen to the right supply pressure.
There are four main electrolysis technologies, all similar in some ways, but unique in others. Each has an anode and cathode separated by a membrane or diaphragm. The overall chemical reaction is the same, but different ions participate in the half reactions occurring at the anode and the cathode. Alkaline has the longest history of industrial operation, while proton exchange membrane is a newer alternative. Both of these technologies, though, have sufficient operating experience to be considered mature and reliable options. Solid oxide and anion exchange membrane technologies are much newer options, with limited commercial experience. As such, these are still considered developing technologies. Next, we'll take a little deeper look at each of these. First is alkaline water electrolysis. This is a low temperature technology that uses a solution of potassium hydroxide at about 25% concentration as the electrolytic fluid. Each cell consists of two electrodes using nickel-based catalysts with a diaphragm separator between. The diaphragm acts as a gas separator only, while the electrolyte allows for migration of the hydroxide ions. Historically, the diaphragm was an asbestos-based material, but due to the health hazards associated with asbestos, it has been replaced with polymeric materials, such as zircon. Alkaline electrolyzers are robust and mature, with low corrosion levels and long run times. They have the lowest capital cost for the stacks themselves, owing to the more common materials of construction required compared to other technologies. It should be noted, however, that capital cost for the overall system needs to be evaluated on a case-by-case basis, as there is some additional complexity with alkaline systems compared to others. Additionally, alkaline technology offers the highest efficiencies currently commercialized. These cost considerations make alkaline the incumbent technology for large facilities. Some drawbacks to the technology are slower response times and lower current density compared to its primary competition. Response rates impact startup time and ramp rates, which may be particularly relevant when coupled to inherently variable renewable energy sources like solar and wind. Current density impacts the physical size of the system required. Additionally, though pressurized designs do exist, most commonly they're operated at atmospheric pressure, which will impact the compression equipment and power required. Shown to the right are two examples of commercial alkaline stacks. While these generally use the same components, you'll notice some differences, including the shape of the cells, ability to access individual cells, and how the stacks are pressed together. Proton exchange membrane technology is also a new low temperature system. It is a newer technology than alkaline, but is fully commercialized as well, with a good track record of operation. As the name implies, a proton is the conducting ion compared to the hydroxide ion in alkaline systems. Rather than having a liquid electrolyte, the solid diaphragm, or membrane as it's called, acts as both the gas separator and the electrolyte. It is usually a chemically stable, sulfonated tetrafluoroethylene-based copolymer, such as naphthalene. The electrodes make use of noble metals, such as platinum, iridium, and ruthenium. Most often, PEM electrolyzers run at approximately 30 bar, but both higher and lower pressure designs exist. Elevated operating pressure reduces compression requirements, and in some cases may eliminate compression entirely, depending on the end usage. Current densities are high, allowing for more compact systems as well. They are very dynamic systems, handling varying loads quickly, including extremely low loads and even short-term overload conditions above the design capacity of the unit. This flexibility fits well with inherently variable renewable energy sources and can be used for ancillary electric grid services, such as voltage and frequency regulation. Finally, owing largely to the lack of caustic system, the arrangement is relatively simple, making it a good fit as a plug-and-play containerized solution. That said, currently they are more expensive than alkaline and normally require a higher energy input per unit of hydrogen. I would again emphasize, though, that the system must be looked at holistically, including any compression requirements for a proper assessment of the total system efficiency. Additionally, while PEM is a commercial technology with a long history, there is less experience than alkaline and its related forerunners. In contrast to alkaline and PEM technologies, solid oxide electrolysis, or SOEC, operates at very high temperature. For this reason, it is sometimes referred to as high-temperature steam electrolysis. Similar to PEM, there's no electrolyte solution. The membrane is a ceramic oxide and acts as both the electrolyte and the gas separator. Here, oxygen ions migrate across the membrane. The electrodes are typically a metal ceramic material for the hydrogen side and a perovskite type, such as lanthanum, strontium, cobalt, ferrite for the oxygen side. The thermodynamics of water electrolysis allows for lower electrical input at higher temperature. This leads to high efficiency. A portion of the reaction energy can be supplied thermally rather than electrically, making it a good fit for use in industrial applications with waste heat. Solid oxide electrolysis cells have another interesting and unique feature. These systems can also electrolyze carbon dioxide to produce carbon monoxide, or electrolyze carbon dioxide and water together to produce syngas. This has some important implications as we look for ways to utilize CO2 captured from existing processes and think about how a circular economy might work. Like many things though, while high temperature opens some doors, it creates its own challenges when we look at things like thermal cycling of the unit. Most importantly though, is that there's limited commercial experience. We expect the next 10 years to be an exciting time for this technology as it transitions from the demonstration level into full commercial status. Anion exchange membrane technology is another low temperature route. This technology is looking to marry the best of alkaline and the best of PEM into a single offering. Structurally, it's similar to PEM, but uses a divinyl benzene polymer membrane. Like alkaline though, an electrolyte is often used. This electrolyte wets the anode side where oxygen is produced. The electrodes themselves are nickel-based. The electrolyte used is typically a weak potassium hydroxide solution, around 1 weight%, versus the higher concentrations used with alkaline systems. This KOH does not circulate to the cathode side where hydrogen is produced, ensuring high purity production of hydrogen from the cell. Unlike PEM, the electrodes do not require noble metal catalysts. That said, this is the least mature technology discussed so far. It is currently manufactured by only one company with modules in the single-digit kilowatt size range. There also remains concerns about the robustness of the technology, potentially resulting in low stack lifetime.
Now we will discuss the current global electrolysis capacity, what the expected capacity might be for the future, and the cost involved in producing green hydrogen. Let's talk about how the electrolysis capacity has evolved over the last 10 years and what the expected increase in capacity looks like in the coming 10 years. Although we see announcements of hundreds of megawatts or even gigawatt scale plants, like the one in NEOM in Saudi Arabia, we should be aware that the current global electrolysis capacity is rather limited, with over 110 megawatts having 60% of that capacity installed in Europe. If we look forward at the expected capacity increase in the coming 10 years, the picture is totally different. Goldman Sachs estimates that the installed capacity by 2030 will be 33 gigawatts, and that is only accounting for the announced projects by summer 2020. How many new projects will soon be announced, especially considering that the European Union green hydrogen target is 40 gigawatts by 2030? We don't know for sure, but something we certainly know is that green hydrogen capacity is going to increase drastically in this decade. To give the audience a concrete figure, 33 gigawatts of capacity is equivalent to producing 5 million tons of hydrogen, which is about 7% of the current global pure hydrogen capacity. Let's now try to understand the cost of green hydrogen. Probably this is one of the most discussed topics when thinking about green hydrogen, and that is the production cost. In the next 2 slides, I will discuss the CAPEX and the OPEX elements of green hydrogen facilities. When we compare the electrolysis system CAPEX, there are certainly 3 figures accepted in the industry. One being $750 per kilowatt of electrolysis capacity for alkaline technology, $1,000 per kilowatt of electrolysis capacity for PEM technology, and $2,800 per kilowatt of electrolysis capacity for solid oxide technology. There is no significant difference between alkaline and PEM, but we can conclude that alkaline is more cost-effective than PEM for large-scale facilities. Solid oxide technology is simply too costly now for large-scale installations. In the last decade, wind, solar, and batteries have seen a significant drop in manufacturing cost due to wide deployment of these technologies. We can expect something similar to happen with water electrolysis technology. Here, the Hydrogen Council did a very good job analyzing the different scenarios depending on different learning rates. Learning rates describe how the cost of a technology decreases as the production output increases, due to factors such as learning by doing and economies of scale. The Hydrogen Council estimates that potentially the system CAPEX could drop to roughly $200 per kilowatt by 2030 for both alkaline and PEM electrolysis technology. These figures refer to direct cost, including stacks, power supply and electronics, utilities, civil and balance of plant, a term referring to the downstream equipment to purify and dry the hydrogen. In this specific example, the direct costs represent 56% over the total investment cost. The picture looks different when comparing direct cost of the 2 most mature technologies, alkaline and PEM. For alkaline, the stacks, power supply, and balance of plant contributes in a similar way to the overall system cost, whereas for PEM, the cost of the stacks contributes significantly more than the other system elements. That is why efforts will be made not only on reducing the stack cost production, especially for PEM, but also on the other items of the plant, especially for alkaline technology. It is important to note that there are certain costs excluded in these figures, such as installation and assembly, indirect cost, land cost, and others. Typically, the total investment cost can even double when considering all the costs involved, resulting then in values of $1,500 per kilowatt installed for alkaline and $2,000 per kilowatt installed for PEM. If we compare the total investment cost of alkaline technology to conventional steam methane reforming for hydrogen production, excluding carbon capture and storage, currently electrolysis CAPEX is in the range of 5 to 6 times higher compared to SMR technology. By 2030, the comparison might look completely different. If the total investment cost for electrolysis technology really drops to $300-400 per kilowatt, then electrolysis will directly compete from a CAPEX standpoint with SMR technology. Now that we know the CAPEX figures of a water electrolysis plant, let's find out what drives the green hydrogen production cost. This economic model is based on the current conditions in the Netherlands. Clearly, the main cost driver is electricity, accounting for 60 to 70% of the total cost. This value will certainly drop in this decade due to expected lower electricity prices, as well as higher electrolyzer energy efficiency. Then CAPEX comes as the second driver, but we can expect this figure to drop significantly in the coming years due to the automation of the stack production. OPEX is the third driver, and here we refer to not only the cost of water and other chemicals, but also to the grid connection fees, which are typically underestimated in the economic models publicly available. These fees can be quite significant, in the order of $8 to $10 million a year for a 100 megawatt plant. Then we have financing costs and hedging costs, which is typically added by banks for this type of technology. If we consider the potential carbon tax benefits by not emitting CO2, as well as selling the oxygen produced, we end up with a hydrogen production cost of about $3.5 to $4 per kilo of hydrogen. And this is considering optimistic conditions. Typical hydrogen production costs following a conventional route of steam methane reforming is $1.5 per kilogram of hydrogen, excluding any cost associated with carbon capture and storage. Here, I wanted to show you the assumptions made in our model, highlighting the most important, the electricity price of $36 per megawatt hour. Here, there is a lot to discuss. For example, what is the optimum operating time of an electrolysis plant to get the cheapest hydrogen production cost? Because wind and sun are not always available. There are some studies claiming that the optimum is found around 4,000 hours a year, using electricity when it can be purchased at the lowest price. Now that we understand the different cost elements involved in green hydrogen production, let's take a quick look at the projections published by two well-known organizations, the Hydrogen Council and Goldman Sachs. The Hydrogen Council expects that green hydrogen will catch up with gray hydrogen first, potentially somewhere between 2030 and 2035, driven by the increase in CO2 carbon tax, driving the gray hydrogen production cost up over time. Then green hydrogen will catch up with blue hydrogen by 2050, if we consider the worst-case scenario. Goldman Sachs, on the other hand, estimates that green hydrogen will only catch up with blue hydrogen at normalized gas prices, basically an average of gas prices over time, and not at current low gas prices. This will only happen by 2050 if green hydrogen is produced using solar power, which is currently the cheapest source of electricity. The purpose of this slide is to show you that there are many reports out there, and the outcome always differs from each other, depending on the assumptions made. These values are not set in stone. They are estimations, and only time will tell when green hydrogen will become cost competitive with gray and blue hydrogen. We wanted to talk about what are the main aspects to consider when building large-scale electrolysis plants, the available options to store and transport hydrogen, using nuclear power to fuel electrolyzers, and some interesting projects happening within Fluor. In this slide, I wanted to discuss, based on our understanding of the technology and experience in executing large-scale projects, what are the main considerations to be assessed when building large-scale electrolysis plants. The first one is location. Will it be a new facility or integrating within an existing one? Will the plant be close to the renewable power generation or close to the hydrogen off-takers to reduce transportation costs? If a constant supply of hydrogen is required downstream, is there availability of existing hydrogen backup, either by gray or blue hydrogen? The second one is power generation. Will the power be generated from solar, wind, hydro, nuclear, or potentially a hybrid power generation system? It needs to be considered that by nature, wind and solar power generation is intermittent, and typically the operating hours lies in the range of 3,000 to 5,000 hours for plants connected directly to wind or solar farms. In addition, will the plant be connected to the grid, probably not always knowing if the power use comes from renewable sources? Or will the plant be connected directly to a wind or solar farm and only operate when the wind is blowing or the sun is shining? The third one is technology evaluation. Here we need to consider several factors, such as technology cost, and ultimately project financing, and how to reduce the risk for funding, perhaps creating strategic partnerships to make the project bankable. Other aspect is technology performance in terms of maturity, reliability, and energy efficiency. Other factors are also the plot space required, the lifetime of the stack, how often it needs to be replaced, and other maintenance requirements to run the plant. The fourth consideration is the hydrogen itself. Will the hydrogen be used locally, or will it be exported elsewhere? Will the hydrogen be sold as such, or further converted into ammonia, methanol, or other fuels? If hydrogen needs to be transported, which of the multiple available options will be considered? I will briefly discuss this topic in the next slide. The fifth one is the plant design. Will the plant be built as a standardized design, or does it need to be customized, for example, to operate at higher pressure? And last but not least, this technology requires large amounts of water. Therefore, water availability needs to be assessed. Is there a good quality water source available nearby, or a desalination plant is required to get sufficient water? These are the 6 considerations to be carefully evaluated at an early stage when building large-scale electrolysis facilities. In this presentation, we also wanted to touch on hydrogen storage and transport, although we must say that this could be a topic for a separate webinar by itself. When transporting or storing hydrogen, there are a number of possibilities to be evaluated. Here I will briefly mention the different options. We can transport hydrogen using existing gas pipelines with minor modifications. There are many studies currently looking at this. The main conclusion is that hydrogen can be blended with natural gas in existing pipelines, up to 15 to 20 volume percentage, easily helping to reduce carbon emissions. Above that threshold, major modifications are required. We can store hydrogen as liquid hydrogen at cryogenic conditions or minus 253 degrees C. We can store hydrogen as compressed gas in the range of 200 up to 700 bar. Here are more options. We can store and transport hydrogen as part of an organic molecule, what's known as liquid organic hydrogen carrier. Basically, an organic molecule is hydrogenated at the hydrogen production site. Then the hydrogenated molecule, in liquid form, is transported using existing gasoline or diesel infrastructure. And finally, the molecule is dehydrogenated at the hydrogen off-taker site, sending the liquid organic carrier back to the hydrogenation facility. We can follow a similar approach as the one described by producing methanol or ammonia. Salt caverns can also be used to store hydrogen, with many studies currently investigating this concept. Once again, the Hydrogen Council did an excellent job summarizing the cost of transporting hydrogen, depending on the distance. For short-range distance, pipeline is the most cost-effective option, whereas for long-range distance, transporting hydrogen either as ammonia, liquefied hydrogen, or as a liquid organic hydrogen carrier still remains a costly challenge, adding on average $2 to $3 more on top of the production cost.
Goes without saying that producing green hydrogen via electrolysis will take an enormous amount of clean power. To replace current pure hydrogen demand of approximately 75 million tons per year, without consideration for emerging markets or growth, requires an annual power input on par with the total annual power demand for all of Europe. This is roughly 2,200 gigawatts of solar PV capacity or 1,300 gigawatts of wind. As a little perspective, the current global operating capacity for solar PV and wind are each around 750 gigawatts. Looking ahead to 2050, with potential hydrogen demands over 500 million tons per year, the power requirements are now on the scale of the annual global power consumption we have today. While solar and wind additions are robust and will play a major role in the energy transition, there are still some fundamental challenges that remain. Low capacity factors necessitate large installed electrical generation capacity, but also increases the installed electrolysis capacity required, unless, of course, battery storage is used to level out the renewable generation. Considering these things, proponents of nuclear energy see a natural fit with hydrogen, even more so if high-temperature steam electrolysis technologies such as solid oxide are successfully deployed. And while nuclear-based hydrogen has claimed pink as its hydrogen color of choice, from a carbon intensity perspective, we are really still talking about green hydrogen. With this approach, a base load of large-scale hydrogen could be produced with a fraction of the land usage. Studies on the NuScale small modular nuclear reactor being developed by Fluor indicate required land use is close to 500 times less compared to solar PV. Putting it into perspective, a nominally 1,000 megawatt NuScale facility would fit comfortably on the Disneyland Park property located near Los Angeles in the city of Anaheim. Meanwhile, considering the low capacity factor and its distributed nature, a solar-based system producing the same amount of hydrogen would need to cover the entire city of Anaheim. Shifting gears from very large to very small, I wanted to highlight an exciting demonstration project Fluor is involved in. California has long been a leader when it comes to clean energy, including green hydrogen. In addition to the growing network of hydrogen fueling stations in the state, we see industry stepping forward as well. SoCalGas is the United States' largest natural gas distribution utility and has committed to net zero emissions in operations and delivery of energy by 2045. Fluor is supporting SoCalGas on multiple fronts. One of these projects is called the H2 Hydrogen Home, which will showcase the role hydrogen must play in attaining California's goal of carbon neutrality. The project will include solar panels, an electrolyzer, a battery energy storage system, hydrogen storage, and a hydrogen fuel cell integrated together into a microgrid for the home. The demonstration will convert solar energy into clean hydrogen, which can be stored, blended into the natural gas supply, and used in the fuel cell for the home's electricity use. Any excess energy will then be exported to an existing SoCalGas commercial facility, further offsetting grid power.
Finally, we wanted to show you a very interesting project in the Netherlands in which Stork, a Fluor company, has been working for the last couple of years. This project was supported by the European Union as well as local organizations, and even the King of the Netherlands, who you can see here standing next to Willem Hassenberg from Stork. The project was about demonstrating the feasibility of using hydrogen for residential heating by implementing hydrogen boilers. The study assessed the installation of an electrolyzer to supply hydrogen to 100 new homes, and currently they are busy with the implementation. In this study, it was also assessed if existing homes can use hydrogen as a replacement of natural gas, proving that it is indeed feasible to use existing gas infrastructure with hydrogen boilers. The existing gas pipelines will need to be carefully evaluated from a metallurgical perspective to deal with a higher concentration of hydrogen at an initial stage and ultimately with pure hydrogen. Ladies and gentlemen, it is time to wrap up. We wanted you to take the following messages home. Hydrogen is important and will play a key role in hard to decarbonize sectors, such as heavy-duty transportation or high-temperature operation in industry. Electrolysis is not a new technology, but its application for on-purpose hydrogen production and gigawatt-scale implementation is new. Electrolysis capacity will expand rapidly over this decade, from 100 plus megawatt to many gigawatt by 2030. ALKALINE generally shows the lowest CAPEX and OPEX, especially for large baseload plants, but PEM technology is not far behind, and it has its own advantages. Whether large or small scale, Fluor has the right skill set to manage and implement not only water electrolysis plants, but also hydrogen logistics, infrastructure, and compression stations in greenfield or brownfield applications. With that, I would like to thank you all for joining the webinar, and now we look forward to your questions.
Thank you, Javier and Patrick and Toppy. We have a lot of questions that have come in already, and we have about 15 minutes remaining, so we're going to try to get through as many as possible. All right, so the first question is, can the lack of availability of water be a problem in the future? And what quality of water is needed?
Yeah, I will take that question. Yeah, so indeed, studying the availability of a water source nearby is extremely important, although building pipelines to transport water is relatively cheap. And yeah, for running water electrolysis plants, you need ultra pure demineralized water quality. And this is very important to avoid the elements of the stack to deteriorate too fast. And depending on the type of water you have, if you have tap water, you will need a pretreatment step such as ion exchange, also known as electrodeionization. And if you have seawater nearby, you will need another different type of pretreatment, such as reverse osmosis, to ensure that the electrical conductivity of the water is in the range of 1 microsiemens per centimeter for alkaline technology. And if it's for PEM technology, you will need to go even deeper into 0.1 microsiemens per centimeter.
Thanks, Javier. Right, the next question for Patrick. What technology in the supply chain exists for transportation of green hydrogen to service markets such as the EU from North America? Is the infrastructure similar to LNG?
Yeah, transportation is certainly, especially between continents, is a grand challenge for hydrogen. And there's a lot of people looking at it right now. There's some demonstration projects between Australia and Asia, Australia and Japan specifically, where they're looking to transport liquid hydrogen. That would probably be your biggest similarity to LNG, I guess, if you will. But those demonstrations are much smaller, and there's not an established infrastructure. In other parts of the world, they're looking at things like converting hydrogen to ammonia, or the liquid organic hydrogen carriers like Javier discussed, as a way to more easily transport the hydrogen long distances. But that's certainly a big cost area, and there's not a strong infrastructure already in place for those activities.
Thank you. So we've had a couple questions come in about the cost. And so the next question I think either of you could answer is, what is the cost of hydrogen and its energy output when compared to traditional oil and gas?
I can take a stab at that. So, think of hydrogen. We like to talk about hydrogen in kilograms, and 1 kilogram of hydrogen is roughly equivalent to 1 gallon of gas in terms of its energy content. So you can make that connection there. The cost, it depends on what you're using it for. We kind of think of a willingness to pay for different markets. If you're using hydrogen as fuel gas, then it's going to have a fuel value, right? And the cost demand is going to be very low. We don't want to pay a lot for fuel gas. Whereas, if we're looking at chemical feedstocks, maybe it's a little more. Transportation fuels, maybe a little more even. So, more near term, you're looking at costs being able to displace maybe diesel fuels and things like that. But we really need to see over the coming decade the cost drive, the CAPEX drop, and the OPEX continue to drop, so that we can be a little more competitive in more markets.
Thank you. Now, I think either of you could take this question as well. From a technology point of view, where do you see the biggest challenge, and what will be required to resolve this even faster than what we're doing today?
Yeah, I can take that one. I think the biggest challenge is getting the technology to be implemented at a large scale. And we have seen that there are now many announcements to install and build even in the gigawatt scale facilities. But so far, we don't have experience with this kind of a scale globally. And I believe the largest plant currently is in the range of 20 megawatt. So we really need to work on what are the challenges to get to the gigawatt scale, and that will definitely help in reducing the cost of this technology over the coming decade. So that's what I will say, getting these plants to a much larger scale to help reduce the cost.
Yeah, and I would add the vertical integration that we'll need is going to be a challenge as well, just from a cultural point of view. Many companies at least are used to working within their slice of the supply chain, and making green hydrogen a reality. I think we're going to see a lot more vertical integration, where you've got the power generation and the hydrogen production and the users, especially in the industrial applications, more together than they have been in the past.
Thank you. So this one's for Patrick. Considering the main end users of hydrogen will be cars, planes, and power generation, are there policies in North America in place to allow this? And have these end user companies already invested in hydrogen technology?
Yeah, so transportation is certainly expected to be a big chunk of the demand. There's differing opinions on which areas of transportation will benefit most. So far, the biggest foothold is, maybe a small one, but there's quite a few hydrogen forklifts out there, especially in North America, but around the world as well. And as far as policies supporting that, it's very regional at this point. I talked a little bit about California. California has put a lot of money in developing the hydrogen fueling infrastructure, and the number of stations popping up shows that. And there are other regions where we see similar things going on, but so far it's a bit patchy. I think moving forward, as more and more governments talk about cost of carbon and carbon taxes or carbon border adjustments, whatever method of costing carbon you want to look at, I think those policies will support further development of some of these technologies.
Thank you. Another question. Do you see any problems related to safety when hydrogen is used? It's a small gas, leaks easily, and when it comes into contact with air, of course, it can undergo an explosive reaction. So how are we looking at solving this?
Yeah, hydrogen safety is, front and center, right? It's safety in everything we do. And while hydrogen, yes, it is a small gas and it does have a tendency to leak through flanges and things like that. It's, especially in industry, it's well understood. And, we talked about transportation. There's been a lot of study around that, around the storage in the tanks. I will say that a big benefit to hydrogen is that it is a light gas. So if there is a release or a rupture, it'll dissipate up into the air very rapidly. You're not going to have cooling of the gas where, we see some of these major industrial accidents. Oftentimes it's because there's a vapor cloud that's been pooled and then detonates. That's extremely unlikely with hydrogen unless you're in a contained space.
Yeah, and also adding on what Patrick said, at least I can speak from the European perspective. Here we are working hard to get the right standards to transport hydrogen on pipelines, because it is quite a challenge if you have countries with different safety standards. So I think now there is quite some work put into getting to those common standards so that we are all on the same page on this topic.
Thank you. Next one for you, Javier. How does the price of hydrogen with respect to production vary with capacity?
Yeah, that's a good question. So when it comes to production of hydrogen, following the green hydrogen route, you don't get much benefit in terms of going for a higher, let's say, capacity plant at the moment. So it scales up by numbering up. So the price is pretty much the same for your stacks. So either you install 100 megawatt, so you are looking at 150 million euros in this case plant or dollars, depending on the type of technology. But if you go for, let's say, 1 gigawatt, you are looking at 1.5 billion. So at the moment, what will help reduce the cost is really scaling up the manufacturing production, and rather than choosing to go for a larger hydrogen installation. If that answers the question.
Thank you. Questions keep rolling in. So here's the next one. On slide 33, Patrick, is there a plan to take the SoCal gas home model option and roll it out on a more global basis?
Yeah, I mean, certainly the concept is that it's a demonstration and a model for the future. From a gas company's perspective, selling methane in a world where we don't like carbon anymore is certainly a challenge. And we have to meet people's energy needs, right? No matter how good we feel about the environment, it's going to be hard for people to set down their iPhones and their computers and things like that. So the question is, how do we make this energy transition robust without sacrificing major quality of life? So yes, it's intended to be a demonstration, but looking forward down the line, how does this apply to greater communities? With this project in particular, the idea is, what does it look like maybe in a condominium complex or a retirement community, or something like that, where you have, just like you have a clubhouse or a central pool that everyone shares, maybe you have a central solar system and central hydrogen system that services a small community. So those are kind of the thoughts that are going on.
Yeah, it's pretty fascinating, exciting for the future. All right, both of you might have a perspective on this question. This will be the last one for today. Does alkaline technology produce any byproducts or waste products, and how could these products impact the environment?
Yeah, I can start, give it a try, and then Patrick can perhaps add. So when you have when you split water, so clearly you produce hydrogen and oxygen. So if you are specifically referring to alkaline technology, you also need a solution of potassium hydroxide. That's what's most commonly used in industry. Of course, you have a small leakage of this solution over time, so you need to make it up for it. Another considered as byproduct is oxygen. So each kilo of hydrogen that you produce roughly results in about 7.5 to 8 kilos of oxygen. So you can call it a byproduct, but there are certain industries that will be happy to take that, such as the steel industry. I'm looking further down the line. Yeah, you will have also some wastewater that will come out of your process. That you need to find a processing facility for it. Besides that, you have waste heat, if you can call it a byproduct. But that's also something that you can even look into the integration into the district heating.
Yeah, I mean, speaking about alkaline specifically, I think Javier touched on all of them, but probably the key one that requires some, degree of management is the alkaline solution, which, does have to be changed on some periodic basis.
All right, thank you. Well, we're going to wrap up, and there were several more questions that we weren't able to get to today, but we'll be sending out a recap email with further answers next week. At this point, I'd just like to announce that to thank the audience for coming and let you know that we'll be hosting our next webinar on Thursday, May 13th at 10 a.m. Central, where Fluor Fellows Sanjeev Dabi and subject matter expert Katie Johnson will talk about transforming waste to green energy through biomass gasification. So keep in touch with your Fluor contacts, follow our social media postings, or head to the Innovation Builders page on fluor.com to register for this or other future webinars. We really appreciate your attention and thank you for dialing in today. Again, we'll send out a compiled list of Q&As within the next few days, and you can expect to see the webinar recording available on demand middle of next week at fluor.com. If you have any questions or require any additional information, you can email innovation.builders@fluor.com and someone from our team will get back to you. On behalf of all of us on the Innovation Builders team, we thank you again and hope you have a safe day.